Welcome to the Royal Swedish Academy of Sciences and this press conference about the Nobel Prize in Chemistry. It's good to see so many familiar faces here also today, and let me also extend a special welcome to all of you who are watching this press conference on the internet or on TV. I'm Göran Hansson, Secretary General of the Academy, and with me today are two members of the Nobel Committee for Chemistry. On my right, Professor Pernilla Vittung-Stavsede, and on my left, Professor Peter Schomfei. The Academy met in session this morning, again, now to decide on the Nobel Prize in Chemistry, and we are now ready to announce the result to you and to the world. I will read the announcement, first in Swedish, then in several other languages. Professor Vittung-Stavsede will make some comments on behalf of the Nobel Committee, and Professor Schomfei will explain the discoveries behind the prize to us. This year's Nobel Prize is about an ingenious tool for building molecules. Årets pris handlar om ett genialt verktyg för att bygga molekyler. Kungliga Vetenskapsakademin har idag beslutat att utdela 2021 års Nobelpris i kemi gemensamt till Benjamin List och David MacMillan för utveckling av asymmetrisk organokatalys. The Royal Swedish Academy of Sciences has today decided to award the 2021 Nobel Prize in Chemistry jointly to Benjamin List and David MacMillan for the development of asymmetric organocatalysis. Die Königliche Schwedische Akademie der Wissenschaften hat heute beschlossen, den Nobelpreis für Chemie des Jahres 2021 gemeinsam an Benjamin List und David MacMillan für die Entwicklung der asymmetrischen Organokatalyse zu verleihen. L'Académie royale des sciences de Suède a décidé ce jour d'attribuer le prix Nobel pour chimie 2021 conjointement à Benjamin List et David MacMillan pour le développement d'organocatalyse asymétrique. Korolevskaya Akademia Nauk решила сегодня присудить Нобелевскую премию по химии Benjamin List и David MacMillan за развитие асимметрическая organocatalysa. That was the announcement, and now we have some biodata about the new Nobel laureates. Benjamin List was born in Frankfurt am Main in Germany in 1968. He got his PhD from the Goethe Universität in Frankfurt, and he made some of the key discoveries that are being awarded today when he was at the Scripps Research Institute in San Diego in the United States. He is now director at the Max Planck Institut für Kohlenforschung in Mülheim an der Ruhr in Germany. David MacMillan was born in 1968 as well, in Bells Hill in the United Kingdom. He received his PhD at the University of California at Irvine. He made some of his key discoveries when at the University of California, Berkeley, and he's currently with Princeton University, also in the United States. So with that, I'd like to ask Pernilla Vittung-Stavsede to make some remarks on behalf of the Nobel Committee. Pernilla.
Thank you, Göran. I'm very honored to introduce this year's Nobel Prize in Chemistry. The prize is about making chemical molecules, and the laureates have developed a truly elegant tool for this, simpler than one could ever imagine. The world is full of molecules, from simple ones, such as the oxygen that we breathe, to complicated pharmaceuticals that cure diseases. Living organisms, like humans, are made up of an astronomical number of molecules of different complexity. In fact, all kinds of materials, plastics, perfume, food flavoring, batteries, drugs, are molecules. To make molecules, we need to link individual atoms together in specific arrangements. That is not an easy task. Most chemical reactions are very slow, so we need to help them. A catalyst is a substance that drives reactions but is not involved in the reaction itself. So up to year 2000, we only knew about two forms of catalysts: enzymes that speed up, in essence, all chemical reactions in living organisms, and metal complexes. But in year 2000, everything changed. Then Benjamin List and David MacMillan independently reported that you can use small organic molecules to do the same job as big enzymes and metal catalysts in reactions that are precise, cheap, fast, and environmentally friendly. The discoveries initiated a totally new way of thinking for how to put together chemical molecules. This new toolbox is used widely today, for example, in drug discovery and in fine chemicals production. It's already benefiting humankind greatly. Thank you.
Thank you, Pernilla. Now the word goes to Peter Schomfei, who will explain the science behind the prize to you. Peter, the floor is yours.
Thank you, Göran. Okay, so I would like to start to introduce you to one of my co-workers who is working all alone in his office one early morning. But please look carefully at the slide. Is he all alone? No, of course not. He's surrounded by friendly molecules, molecules that makes his coffee taste great, that keeps his food fresh, smoothing his skin. And as you probably can see from the picture, he's working on a very important press conference, so he's a bit stressed. So he also needs some molecules to relieve him from his headache. Now, some of these molecules are isolated from natural sources, others are man-made. And the question is, how do we make man-made molecules? Well, the answer is straightforward. We make them from simple building blocks and forging them together. But to be able to do that, we need two things. We need good and powerful reactions, and we need good methodology. And this year's prize is about the development of a new, powerful methodology for making organic molecules. Before we proceed to discuss the actual prize, there's one more thing we need to know about organic molecules. Some molecules are like our hands. They are non-identical mirror images of each other. So our hands, they are both hands, but they are not identical. They are simply mirror images of each other. And one such molecule, just to give you an example, is limonene. One mirror image of limonene smells like orange. The other one smells like lemon. Now, what does that really mean? It means that our bodies are capable of differentiating between the two mirror images. And if you don't believe me, I have the two different mirror images here, and you're welcome to smell them afterwards, and I can guarantee you that you will smell the difference. Now, if our bodies can differentiate between two such simple molecules, then of course it will be able to differentiate between the mirror images of drug molecules that can have a different physiological response. And it then becomes important to selectively be able to manufacture only one of the two possible mirror images. We have two techniques available for that. One is metal catalysis, and the other one is using enzymes. This year's prize is about developing a new methodology for selectively making one of the two possible mirror images of a molecule. And it is done by using designed small organic molecules, and it's referred to as asymmetric organocatalysis. It started by two key observations in the year 2000 made by this year's laureates, and I will discuss them separately. So Benjamin List started with a reaction that is known as the Aldol reaction. It's an important reaction in organic chemistry where two molecules are forged together and at the same time creating a new carbon-carbon bond. And the two product molecules are formed as two different mirror images of each other, non-identical. Now, this reaction is ongoing constantly in our bodies, where it's catalyzed by an enzyme called aldolase A. Now, this is a huge enzyme consisting of about more than 350 amino acids, but it's only 3 amino acids that are responsible for the catalytic activity. It's a lysine, a glutamic acid, and a tyrosine. And Benjamin List asked, is all this other stuff really necessary, or can we simplify it? And he managed to show that indeed we can. And only a single amino acid is necessary to catalyze this reaction, and that is a proline, a molecule that we all have in our bodies. So he showed that this particular problem is possible to simplify. We can identify a small organic molecules that catalyze the Aldol reaction. MacMillan's entry to this problem was different. He was interested in a reaction that is called the Diels-Alder reaction, which is a very powerful reaction in organic chemistry where 2 molecules are forged together and forming a 6-member ring. And 6-member rings are ubiquitous structures in organic chemistry. They are everywhere in our bodies, in nature, everywhere. So it's an important reaction to make them. The problem with this reaction is that it is rather slow. And one type of catalysts that speed up the reaction by activating one of the substrate's molecules is shown up here. And David MacMillan wondered, this catalyst has 2 problems as he viewed it. One is that it contains a metal atom, and the other one that it's so sensitive, so it's never used in industry. Now, is it possible to get rid of the metal atom and make something that is more stable? And indeed it is. He designed a molecule that is called an imidazolidinone and shown that that is possible to use to activate one of the substrate molecules to form an intermediate that's called an iminium ion. And then it's so activated so the reaction will proceed and we will form the product and preferentially one of the 2 possible mirror images. This year's laureates showed that it is possible to design small organic molecules to act as asymmetric catalysts. They rationalized their finding, which is very important, and this resulted in an immediate response and activity from the scientific community. And as a result, today we have a large number of organic catalysts available, and we also have a large number of reactions which they catalyze. Now, what is the consequence of this? The consequence is that we now have a new powerful tool. New powerful tool available for making organic molecules. Compared to metal catalysis, organocatalysis is a more sustainable alternative. It has been estimated that catalysis is responsible for about 35% of the world's GDP, which is a pretty impressive figure. And then if we have a more environmentally friendly alternative, it's expected that that will make a difference. I will give you 2 examples of that. The first one is a molecule that is called oseltamivir, which is the active ingredient in an antiviral drug of much current interest. The organocatalytic route to oseltamivir consists of 5 reaction steps, while the current production route to this molecule consists of 12 reaction steps. And then we need to know that each reaction steps make an environmental impact, and it's important to reduce the number of steps it takes to make a molecule. So comparing 5 to 12, that is a significant difference. I will give you one more example, and that is the molecule strychnine. Now, as you all know, strychnine is a very poisonous molecule, and you would ask, naturally, who in the earth is interested in making strychnine? And the answer is, well, nobody, of course. But this molecule has a significant interest to organic chemists because it has a very complex structure, and it is then a good measure to show how efficient our methodology is by comparing it to previous methods of making it. And the organocatalytic route is 7,000 times more efficient in making strychnine compared to the original route, which is once again showing the power of this methodology. So in conclusion then, we have a new tool available in organic chemistry, and this is of the greatest benefit to humankind. Thank you.
Thank you very much, Peter, for that excellent presentation. And now it's time for questions. And I think we may have one of our new Nobel laureates with us on a phone line. Dr. List, are you there?
Yes, I'm right here.
Great. Thanks for joining us at the press conference. I gather you are on vacation with your family right now.
Yeah, I'm actually in Amsterdam. We visited a great concert in the Concertgebouw, and we have a wonderful day. And I absolutely didn't expect this huge surprise. And yeah, I think you really made my day today. Thank you.
Good to hear. So now questions from the media representatives. Thomas von Heine, Swedish TV, please.
Sorry. Herzliche Glückwünsche, Herr Doktor. This is Swedish television.
Oh, vielen Dank. Tack så mycket.
We'll do it in English. I think that's required.
Yeah.
It says it's about 20 years ago that you found these catalysts. Could you briefly summarize where are you today in comparison to 20 years ago?
Yeah, that's a very good question, because at the time, and sometimes people wonder, why does it take so long for a discovery to be recognized? And in this case, our early days catalysts were, in comparison to what we have, like maybe 1 million times less efficient. The real, in my opinion, the real revolution of what we have, of our discoveries, is only sort of surfacing now with these extremely reactive organocatalysts that can do stuff that you cannot do with enzymes or even with the most sophisticated metal complexes that people have developed before. So it's a matter of degree, but also a matter of sophistication, I would say.
Great, thank you. So first the breakthrough and then continuous improvement and steps forward.
Yeah, exactly.
More questions? Yes, please. Gentleman from DPA.
Dr. List, herzlichen Glückwunsch auch von der Deutschen Presseagentur. I do this in English.
Vielen Dank.
What was your first feeling when you got this famous telephone call from Stockholm this morning?
I thought somebody's making a joke with me. I was sitting at breakfast with my wife, and sometimes she says, "Did you look at your phone if somebody called from Sweden?" But today we didn't even make the joke, and we certainly didn't anticipate this, right? And then Sweden appears on my phone, and I look at her, she looks at me, and I run out of the coffee, and indeed, that was the amazing call. I mean, I don't know, it's hard to describe what you feel in that moment, but it was a very special moment that I will never forget, for sure.
Thank you. David Keaton, Associated Press.
Hello, David Keaton, Associated Press. Congratulations on this award. Professor, when these discoveries were made 20 years ago, did you realize immediately the impact that this would have? Did you foresee a little bit where this field of studies would go? Or has it surprised you at the same time as science has progressed on through these discoveries over these last 20 years? Thank you.
Yeah, thank you very much for the question. I mean, the thing is, I really felt at the time, I literally felt like I'm the only one working on this. And I didn't know that Dave, also in California, was also working on it. We didn't know from each other at the time. And when I did this experiment, I didn't know what would happen, and I thought maybe it's a stupid idea or somebody has tried it already. And then when I saw it worked, I did feel that this could be something big. That's certainly true. But That this would happen, of course, in that moment, no way. I didn't anticipate that.
It's a great story when research at its best, when it's a sudden breakthrough here. Yes, more questions?
Yeah.
Yes, please.
Congratulations on the prize. My name is congratulations on the prize. My name is Anneli Megner-Arn from Swedish TV4. I wonder, these organocatalysts, how does it work that they only make one of these mirror images and not the other?
Yeah, that's a good question. I mean, this is a mystery that chemists and scientists in general have not been able to answer. Why in the world is biology single-handed? Why do we have this preference in nature? We don't know this. We don't know this until today. That's my honest answer. Sorry. But the molecules that we use, fortunately, we can use them from natural sources. So they have been made from biological organisms, and so they have that property that they have this handedness about them. And that's what we utilize and then in the catalysis, because this handedness is transferred in the catalytic reaction onto the substrates so that you get more of these handed molecules. Yeah, it's a great gift, I would say, that nature provides these molecules for us.
Thank you. More questions? Yes, please, go ahead again, Anneli.
Can I ask one more? I wonder what your favorite catalyst is, and also the favorite product, if you have any of those from your research.
So my favorite catalyst, of course, has to be proline. That was my first realization and understanding, really, what organic molecules could do and the beauty of this molecule. And by the way, it's an edible molecule. So, of course, I already tried it. Even people use it as a food additive. I don't know why, but it's because we make it in our own body. It's completely harmless. It tastes slightly sweet, like my discovery back then, slightly sweet taste. I didn't know what would happen. But my favorite processes are, of course, what we do right now. Right now, this has advanced so tremendously that we have catalysts that do stuff that even enzymes couldn't do, and that really shocks me. And there are many reactions that we currently work on, and they're all my favorites.
Thank you. Yes, please, gentleman over there.
Philip O'Connor, the Reuters news agency. Could I just ask you, what do you think winning this prize will mean for your future research?
That's a good question. I don't know. I was just asking myself this question. What am I going to do now? But I can assure you we have a few more plans. Like I always like to go to the extremes. Can we do things that were just impossible before? And I think this award, of course, gives me this even more of the freedom that I already enjoy as a Max Planck scientific member. We have the freedom really to do whatever we like to do research-wise, and now I feel even freer, if that's the word. And yeah, this is very, very exciting. And I hope I live up to this recognition and continue discovering amazing things. That's at least my goal.
Very good. Are there any more questions to Dr. List? If not, thank you very much, Dr. List, for being with us at this press conference. And once again, congratulations to your Nobel Prize.
Thank you so much. I'm deeply honored.
Thanks. Bye-bye.
Bye.
And now, time for questions to the panel. Do you have any questions for us? Yes, please, David Keaton again. Go ahead.
Thank you, David Keaton, Associated Press. One of the major breakthroughs in the last few years has obviously been the mRNA technology, science behind what has led to some of the drugs we're using that enable us to be all here today in this room. Obviously, I understand that you cannot talk about the other nominations and everything, but personally, from your own perspectives, the science that you've been reading over these past few years, when you've been coming across these papers, these scientific papers, Do you look and stop and think, this is maybe a future Nobel Prize for the years to come?
Do you want to start, Pernilla?
Should I answer that?
Go ahead.
Well, as you say, we can't comment on other people's nominations or possible prizes. But what I want to say is that the work that we do in the committee, we do very thorough analysis and looking back and looking at the discoveries and who made the discoveries. So it takes time because it's very thorough and therefore very slow. So having said that, this is, of course, an extremely important topic that we are thinking about. But there will be more years, more Nobel Prizes.
We've learned in the history of the Nobel Prize that it's best to be very careful and check under each and every stone rather than rush ahead. And that's part of what's built the legacy of the Nobel Prize to what it is now. So I think we'll continue in that way. So stay tuned for future Nobel Prizes. More questions? Usually someone asks me if I've been able to reach both Nobel laureates. Interested? No. We have not been able to reach Dr. MacMillan yet. So I have, over the years, called 52 Nobel laureates. But my 53rd, I had to inform through an email and a recorded message on his cell phone. I hope he'll call me back after the press conference. Any more questions? If not, thank you very much for your interest. Now there will be opportunities for interviews with experts, and our staff members will help you find your particular expert. But thank you for your interest, and welcome back. Bye.
Peter Jean-Fay, can you summarize this year's Nobel Prize in Chemistry for us?
Yes. It's about a new tool for making organic molecules. And it's, if I would summarize it in an easy way, what it really means, think about playing chess. And then you introduce a new player on the chessboard that has new rules. Well, that means that you will think about the game in a different way, and you can execute the game in a different way. And that is the power of new methodology when it comes to organic chemistry. Think and do molecules in a way we couldn't do before.
So there are new pieces and new rules.
Yes, exactly. So organocatalysis is a new player, and then it is up to us who is going to use it to think about how can we use this new tool when building molecules.
And if you had to explain this to a child like 10 years old, what would you say?
I would say that think about, for example, the medicines that you take. Now we have an alternative to make them that is less harmful for our environment than it was before. So even for the whole planet, it will be of benefit. Since when making molecules, it will be a lower impact on the environment.
What actually was the problem that the Nobel laureates solved for 20 years ago?
No, I don't think that you should look at it as they are solving a problem. They are adding something to our toolbox. It's just like the analogy I told you about the chessboard. So you're not solving a problem, you're adding something. So whenever we're going to make a molecule, we have a new tool that we can use to think about how to solve this problem. And then this will be an obvious alternative.
Catalysts have been used for about 2 centuries. So how come this came so late?
I think that sometimes it is like this, that the obvious answers or the obvious solutions are sometimes just too obvious. It's right in front of us, but we don't see them. I mean, I'm an organic chemist. I'm working with small organic molecules every day, but I didn't think of it, but they are all around me anyway. So it was just too obvious, I think. And then what was very important, what this year's laureates did, is that they explained it, they rationalized their findings. And the rationalization was so simple, so it was immediately appreciated by the scientific community, which resulted in what is called a gold rush or an explosion in the area, because now everybody realizes, oh, we can do this, and it's easy to understand, and it's easy to design new things using this simple explanation that they provided.
And this is about asymmetric catalysis. Yes. Can you explain that?
It's like some molecules are just like our hands. They are both hands, but they are mirror images of each other. They are non-identical. And some molecules are just the same. One mirror image will have one effect, and the other one will have a different effect. One example is, for example, the molecule limonene that can be isolated from oranges and lemons. One of the mirror images smells like orange, and the other smells like lemon. That means that our bodies can differentiate between the two different mirror images. And the important take-home message here is that if our bodies can differentiate the smell of these two molecule mirror images, then the same will probably be true for drugs that we take for diseases. And then it becomes important to be able to make only the mirror images of drugs that have the desired physiological effect, and not the other one that can have another effect or have a non-effect.
So you don't want to have both lemons and oranges?
Exactly, because that doubles your exposure to chemicals. So your body has to get rid of the non-active mirror image, and the desired effect will only be of one mirror image. So you double your exposure, which of course is not good for your body.
So in what way does this discovery influence us?
It's influenced us that I would say in two ways. It has already a considerable impact in drug discovery, where we are making molecules in order to identify new potential drugs. There is already an active tool. And then when we want to make a molecule, we have a new alternative. So before we had metal catalysis, we have asymmetric catalysis, and now we have a new tool. And when we are going to make a new molecule, we will evaluate which tool will be most efficient to solve this particular problem. And the more tools we have, the less environmental impact, the more efficient we will be. And this particular tool that we have now, asymmetric organocatalysis, that's a very powerful tool. So that will definitely have an environmental impact in the coming years.
You mentioned also that it's environmentally friendlier
than, for example, metal catalysis, yes.
Why?
Metals you have to get rid of. That's a waste. These catalysts you recover. And sometimes we are using metals like iron that is okay with the environment, but sometimes we are using metals as catalysts that are not okay with the environment. Can we get rid of them and use, for example, organic catalysis instead? That would be a benefit for the environment.
So where are they used now?
I would say they are used not for production yet, because it's still early, but they are used in discovery. So, for example, drug discovery and other discoveries in industry and, of course, in academia.
Can you tell us something about the laureates? Did you talk to them today, this morning?
We only got hold of Benjamin List, and he was extremely happy. I've never heard anybody happy in my whole life. He was absolutely out of his mind. He's 56 years old now, and he said, "Oh, I never dreamed of this. Maybe when I was 80, I could perhaps get it, but now, oh, this is." He was so happy. So you could really hear that he was flying on clouds when Göran talked to him. It was a very great feeling.
Can you tell us what makes you enthusiastic about this year's prize?
Definitely. It is, as I said earlier, it's a game changer because it's an improvement that gives us a new tool, just like the chess game, that is very, very powerful. So I'm excited about this year's prize. And I think the analogy with the chess game is pretty clear, because otherwise explaining organic synthesis, which this is all about, it's rather complex and it's difficult to appreciate for an outstander, but it is just like adding a new chess player that can move in different ways. So it's completely changing the game. So I'm working myself in organic synthesis, and I would say that this is definitely a game changer. It's super in my mind.
Thank you very much, Peter Sonfai. It's a pleasure to talk to you.
Thank you.